Hi everyone, welcome back to my video on the chemistry section of the 2019 Invitational A for Science UIL. And in today's problem, I'll be going over the 20 chemistry problems. So these are the questions from 1 to 9. These are the questions from 10 to 15. These are questions from 16 to 20. So just pause the video, answer all these questions first, and when you're done, I'll show you all the solutions. So for question 1, we're asked to find the molar mass of magnetite. So when we're trying molar mass of any compound, we take the elements in the compound. So in this case, there's 3 iron and 4 oxygen. So when we take the elements, we need to find the molar mass of each of the elements. And luckily, we're given a periodic table. So iron, you have a molar mass of 55.85. Oxygen, you have a molar mass of 16. So go back to that question. So we simply have 3 times 55.85 and 4 times 16. And now you're allowed to use a calculator on the exam. So when you calculate that out, you should be getting 231.55 grams per mole. So that would be the answer for number 1. For number 2, we're asked to perform a combustion reaction of butane. So before we even get started, what is a combustion reaction? Combustion is basically the reaction where a hydrocarbon compound is mixed with oxygen gas to create carbon dioxide gas and water vapor. So knowing this default structure of combustion is what will help you solve the answer. Your oxygen will be the reactant, and the end products are carbon dioxide and water. Now, we know that it's butane, so C4H10. C4H10. For any balancing, with combustion, I would immediately look at carbon first. Looking at carbon, we know that there's 4 carbon on the left side and only 1 carbon on the right side. And so we have to multiply CO2 by a number such that we'll get 4 carbon on the right side. That number will be 4 because CO2 only has 1 carbon, but we have 4 CO2, we'll have 4 carbons on the right, and we have 4 carbons on the left. That will equal out, and there are equal number of carbons on both sides. The next element I would look at would be hydrogen. There's 10 hydrogen on the left side and 2 hydrogen on the right side. What number must we multiply to the 2 hydrogen on H2O to get 10 hydrogen? That would be 5. So we got carbon balanced, we got 4 carbon on both sides, and we got 10 hydrogen on both sides. We're at our last element, oxygen. If we add up all the oxygen on the right side, CO2 has 2 oxygen per molecule. So if you have 4 moles of CO2, we would have 8 oxygen. And H2O, if we have 5 H2O, we would have 5 oxygen. So that would be 13 oxygen in total. And we want to multiply O2 by a number such that you would get 13 oxygen. The thing is, we obviously can't multiply 2 by any number to get 13 because you can't multiply 2 to get an odd number. But what we can do is we can actually multiply the entire equation by 2. Multiply every coefficient except O2 by 2. So let me demonstrate. We have 1 times 2 is 2, so we have a 2 in front of the butane. Instead of 4 CO2, we'll have 8 CO2. And instead of 5 H2O, we'll have 10 H2O. And look what happens when we do that. all the previous atoms will stay the same. Now we have 8 carbon. We have 8 carbon, 20 hydrogen, 20 hydrogen. But now, 8 times 2, we have 16 oxygen on CO2. And 10 times 1, we have 10 oxygen on. We have 16 oxygen plus 10 oxygen. On the right side, we have 26 oxygen in total. What number can you multiply by O2 to get 26 oxygen? 13 times 2 would equal 26. So this is our final balanced equation. We have equal number of atoms on both sides. Now, the question is asking us to add up the coefficients. That's simply 2 plus 13 plus 8 plus 10. That would be 33. So the answer to number 2 is going to be E. For number 3, we're trying to find the best ground state electron configuration for strontium. So let's say it'll be easier if I pull up both the periodic table so I can demonstrate to you guys a bit easier. So the first thing we want to do is identify where strontium is on the periodic table. This is something, the tough part is probably knowing how the atomic symbol of strontium, it would be Sr, and it's going to be right here, element 38. So now we're trying to find the best ground state electron configuration. What does ground state mean? It means there are no excited electrons. So no electrons will be going in a shell that hasn't been filled. So every ground shell below that is going to be filled. So let's look at let's first draw the electron configuration on our own. The fastest way to do that is to first look at what block strontium is located on the periodic table. If you guys don't know what blocks are, this group 1, 2 plus helium is considered the S block. Groups 13 to 18, with the exception of helium, is considered the P block. The transition metals are considered the D block, and the lanthanides and actinides are the F block. So, strontium is in the S block. Let me explain what that means. That means the electron at the very end of the electron configuration is going to be S. That doesn't really help us too much because every single electron here, every single electron has S at the end. But what it does help us is this. Once we know that, let's figure out what the number in front of the letter would be. So in the S block and the P block, the period corresponds to the shell number. So here, strontium, we'll just count by periods. 1, 2, 3. Okay, I'll just count from here. 1, 2, 3, 4. Strontium is in the 5th period, or it's pretty much the 5th row. So I'll just do that one more time. 1, 2. Strontium's in the 5th row, so you would have a 5 in front of the S. 5S. Once again, doesn't help too much because everyone is basically 5S. But here's the thing. Strontium is the second element in the 5S row. So that means it has both electrons in its orbital. The orbital is completely filled. So it has 2 electrons because it's a second one. Like rubidium would be 5s1, strontium would be 5s2. Now we got somewhere because now we know E is the wrong answer. And now we're down to either A, B, C, D. What you need to know now is the electron configuration, this electron configuration chart that you guys should be expected to memorize. It would start off with 1s, because the 1s is the hydrogen and helium. 2s, lithium, beryllium. 2p is from boron to neon. Yes. 3s, 3p, 3d, 4s, 4p, 4d. Let me move this aside here. 4f, 5s, 5p, phi d, 5f. And we can stop there because strontium doesn't go that far. Now I want you to cross through any element going from the top right to bottom left. So we got 1s, and we're filled it. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now look here. We notice something. C. This is a hybrid orbital. C is a hybrid orbital. You have S and P combined into one. That's not how you would write electron configuration, so that's out. We know it's 3s2, 3p6, 4s2. Immediately after 4s2 is 3d10 because of the diagonal line. You would go from here to 3d10. That would make no sense for B to go from 3p6 to 3d10. So B's out. So after 3d10, you get 4p6, 5s2. Now, you're down to A and D. And D is called the noble gas configuration because you're using a noble gas like krypton to replace all the other ones before. So there's one thing is that krypton is 4p6. So krypton consists of everything past 4p6. So the actual noble gas configuration would be krypton with 5s2. But D is talking about 4p6, 5s2. So D would be incorrect. The only option choice would be A. If you want a longer, but I think a little bit easier, if you've never heard of electron configuration before, an easier explanation would be going from left to right in rows. So, actually, I'll keep everything else. You start from hydrogen. This is 1s. Helium, well, that's 1s1. Helium is 1s2. Then you go from lithium, 2s1, 2s2, and then you immediately cross over to the P block. Then you have 2p1, 2p2, 2p3, 2p4, 2p5, neon is 2p6. Then you go to sodium, 3s1, and then cross over again, all the way to 3p6. Now, when you're at potassium, that's 4s1, calcium's 4s2. The D block occurs. And the first row of D block starts at 3, not 4, which is a little confusing. This is why I showed the chart over here, because it does make help me learn this one. But if you just memorize that the first D block is 3 and not 4, it'll make that easier. You continue all the way here with P block remaining 4p6, ending off at krypton. So you know krypton ends at 4p6, and then strontium follows up right after that with 5s2. So everything past that has to be krypton. So the configuration would be krypton and then 5s2. Or if you had drawn the entire thing out, this whole thing would have been krypton and then you have 5s2 at the end. For number 4, we're asked to find which compound contains exactly one unshared pair of electrons. So now we need to know how to draw Lewis structures because this is a crucial skill for this question. I'm going to once again bring up the periodic table because we'll need that to help us draw. And there are a couple of rules for drawing Lewis structures that I'm going to go over. Number 1, we have to find the total number of valence electrons in the compound. So I'll take A, for example, BF3. To find the number of valence electrons in the compound, we need to find the number of valence electrons in each atom and then add them all up. So how many valence electrons are in boron, for example? Well, we know any atom in the first two groups, as well as the last 6 groups, the number of valence electrons they have is equal to their group number. So boron is group 3A. Well, it's group 13, but you could ignore that and just only focus on the other groups, so 3A and 4A and all that to 8A. So boron's in group 3A. That means it has 3 valence electrons. Fluorine is in group 7A, so it has 7 valence electrons, and there are 3 fluorine atoms here, so that would be 24 valence electrons. Now you know the valence electrons, you want to know the central atom. The central atom is always the least electronegative. So the central atom is the least electronegative. So in this case, boron and fluorine, boron is way less electronegative than fluorine. Fluorine pulls electrons way easier than boron would, so boron would be in the center. And now you're surrounded with 3 fluorines. Now you know where the atoms would be. Now let's draw the structures. The next step is to draw a single bond between the center atom and all the other atoms. And remember, a bond is the sharing of 2 electrons. So each bond has 2 electrons. So now we have 3 bonds. That means we used up 6 electrons. And we had 24 to begin with. So how many do we have remaining? We have 18 electrons remaining. And now, once you draw those initial bonds, you want to arrange those remaining electrons on the outermost elements. So remember, each element can hold up to 8 electrons on the outermost shell. At least once you get to this level. There's are exceptions here and there, but for now, any of the outermost elements can hold up to 8 electrons. And each bond is 2 electrons. They're sharing 2 electrons. So each of these fluorine can hold up to 6 more electrons. So we can draw 6 electrons around each fluorine. And 6 times 3, 18. So we got rid of all the electrons. Now, you guys might be asking, what about boron? Boron currently has 3 bonds on it, which means each bond has 2 electrons, so that's 6 electrons. Why doesn't boron want 2 more electrons? Doesn't boron also need 8? Boron's actually an exception to the octet rule, and it actually prefers having only 6. In fact, there are some configurations where boron can have 8, but it instead chooses to have 6. So remember, boron is an exception. So this is the Lewis structure for BF3, and as you can see, there are no unshared pairs. An unshared pair is basically just a lone pair. Like fluorine, for example, has 3 unshared pairs, like each of these 2 pairs of electrons. Boron has none, so you can cross out A. I'll go over the remaining ones a little bit quicker now that you understand. Feel free to put in the comments if you guys don't understand, and I could try to clarify it to you. For phosphorus, hydrogen, we have phosphorus is in group 5A, and hydrogen only has 1 valence electron, 3 hydrogen. There's 8 total electrons. Phosphorus is the central atom because it's less electronegative than hydrogen. Also, wait, one more thing. Keep in mind, this is pretty crucial. Hydrogen can never be the central atom, even if hydrogen is less electronegative. So, though the central atom can be the least electronegative, and it cannot be hydrogen. Now back to the problem. Each bond has 2 electrons, right? So 3 bonds, meaning we're losing 6 electrons. We have 2 remaining. Now, you might be thinking, didn't you tell us to add the electrons to the outermost elements? Again, hydrogen is an exception to that because hydrogen only has 1 shell, and that 1 shell can only contain 2 electrons. And it already got its 2 electrons from the bond. So now we can add these to the central atom. And in the central atom, we have 1 unshared pair. So the answer to this question is going to be B. Feel free to skip ahead. I will just go over C, D, and E just to get you guys a little bit more used to drawing electron configurations. For H2S, hydrogen only has 1 valence electron. We have 2 hydrogen, and sulfur has 6 electrons, 6 valence electrons, because it's in group 6. It's in group 6A. That's 8 in total. Remember, hydrogen can never be central, so that we're only left with sulfur as a central atom. And if we draw a bond between sulfur and hydrogen, we have 2 bonds. And each bond is 2 electrons. So we have 4 electrons total that we just used up. So 8 minus 4, we have 4 remaining electrons. Since hydrogen is full, we're just going to put those 4 electrons on sulfur. Also, by the way, one sec, that's not a double bond. This is the valence electron for H2S. And as you can see, sulfur has 2 unshared pairs, so we can get rid of that. Let's do the same for NO2. Nitrogen has 5 valence electrons, oxygen has 6, and there's 2 of them. You have 17 in total. Nitrogen is the least electronegative out of the 2, so we can do that. And since each bond has 2 electrons, we can rinse and repeat. We have 13 remaining. Throw them on the oxygen. As you can see, after we filled up all the oxygen, that's 6 on each of them, so that's 12 in total. We have 1 valence electron remaining. We can put that on nitrogen. But look here, guys. Nitrogen has 5 valence electrons because 2 of them are in the bonds, so we have 2 bonds, so that's 4, and it has that 1 electron we gave to it. It wants 8. So we can try to get this as close to 8 as possible. That's our goal. Anytime you're in this kind of situation, you want to draw a double bond. A double bond basically is you're sharing 4 electrons instead of 2 because you have 2 of the bonds and each of them shares 2. So remember, the electrons from a double bond has to come from somewhere. So this oxygen will actually lose 2 lone pairs to form that double bond. Now, oxygen still has 8 electrons. 1, 2, 3, 4, and each double bond has 2, so that's 4 there. Nitrogen now has 2, 4, 6 from the bonds, plus this one, lone one, 7. But the thing is, nitrogen wants 1 more electron, but you can't just form another double bond because now that will give him 2 electrons. And now we'll have 9, and that's beyond the octet. Nitrogen cannot expand the octet, so we will... This is actually the Lewis structure of NO2. And as you can see, because nitrogen needs 1 more electron, it will... this is a property of NO2. It will try to take away an electron from an outer source. That's why the most common form of NO2 you'll see is NO2 with a negative sign, because that means it gained that last electron needed to form the octet. And by the way, if you just didn't know, this is the polyatomic ion known as nitrite. So once it gains that last electron, then it will be fully stabilized. Before that, it will be known as what's called a radical, meaning a free radical, which they're compounds that take away electrons from outer sources. That's a good vocab word that you guys might need to know if other chemistry problems will mention that. Our last one is definitely much easier than this one, so this one should be quick. CCH4 is made up of carbon, which has 4 valence electrons, and chlorine, which has 7, and there's 4 of the chlorines. So that's 32 valence electrons in total. Carbon's the least electronegative, so it's in the center, and there are 4 bonds extending from carbon. So that's 8 electrons used to make those 4 bonds, so you can get rid of 8 of them. You have 24 electrons remaining. We can fill each of the outermost atoms with 6 electrons. So that means we use up all 24 of the elements. So this is the most stable structure of CCl4, and obviously there are no unshared pairs on the carbon. So the answer to number 4 would be B. For number 5, we're asked to find absolute zero measured in Fahrenheit. So this one will require a little bit of conversion, but remember the formula that converts between Celsius and Kelvin. So the temperature in Kelvin is equal to 273.15 plus the temperature in Celsius. So 0 Kelvin equals 273.15 plus Celsius. So the temperature in Celsius must be negative 273.15. Now you want to convert from Fahrenheit to Celsius. The formula for that is 9 over 5 times the temperature in Celsius plus 32. So plugging negative 273.15 into that, you would get negative 459.67 degrees Fahrenheit. So the answer to this question is going to be D. For this next question, we're asked, why does the mercury level go up in a thermometer as the temperature rises? Let's get some of the, let's understand how temperature relates to atoms. As the temperature rises, the kinetic energy in an atom rises. So that means the atoms will have more kinetic energy, which means they'll move faster. And what happens when atoms move faster? They're gonna travel through more distances, and they're gonna pretty much expand. Think of all these atoms moving really, really slowly here. They're moving random directions very slowly. Now think what happens when they're gonna start going much, much faster. They're gonna naturally start to expand because of that. So let's look at all the option choices. Because that's how thermometers work, I think that's really just one they were just trying to throw it off, give you only 4 option choices. For B, because heat rises, so as mercury warms up, it rises up the tube. The thing is, they're not wrong with the heat rising, but I mean, that has more to do with air. Like hot air would rise above cold air, and while yes, it would rise initially, like the hot objects would rise because they have a little less density than the cold objects. Once you get to a point, once it reaches equilibrium and the entire mercury is the same temperature, that wouldn't make sense for it to rise continuously. So B is incorrect. C, we know that atoms cannot just expand in size just because they're heated, so C is wrong. For D, the mercury atoms move further apart as temperature increases, increasing the volume of the mercury in the tube. That is true because mercury atoms, or any atom, once it's heated, it starts to spread out. And as for E, some mercury at the bottom of the tube begins to boil, pushing the mercury above it higher up the tube. That doesn't make sense because just like my explanation with option choice B, eventually when everything's the same temperature, there shouldn't really be any one part boiling while the other part isn't. So anything that has to do with heat rising at a certain point is just incorrect. The only option choice is when the molecules start moving further apart from each other. So the answer to number 6 is D. For number 7, we're asked to find under which condition does the ideal gas law begin to fail. To first get started, we have to know what an ideal gas is. An ideal gas is any gas with no intermolecular force, which is basically a force that attracts temporary attractions between two atoms. We don't want any of those. Now, how do we prevent those? Let's think of it logically. When you have two atoms that are very far apart, the force between them is not very strong. They're just too far for them to interact. Think about the gravitational force between objects. Obviously, since we're really, really close to Earth, or we're pretty much on Earth, the gravity between Earth and our body is very, very strong. But if we go very far, we're not going to really feel the effects of gravity from Earth to our bodies because we're just far away. Same thing, atoms work on the same principle. The further they are, the less attractive force they have due to intermolecular forces. So based on the number 6, I told you guys that as temperature increases, the distance between atoms increases. Atoms will start to spread out. So that means the higher the temperature, the further they are. The higher the temperature, the more ideal they are. So what about pressure? Pressure kind of works in the opposite way. Imagine you have a box with all these atoms. And it's a very big box. So atoms have a lot of space to move. Now, what if I compress this box? What if I decide, make it really small? Now the atoms just don't have that much space to move. They're much more pressurized. And since they're so much closer to each other, the intermolecular forces between them will start to be really strong. So at high pressure, so as pressure goes up, the gas becomes less ideal because there's more intermolecular forces involved. So when the ideal gas law begins to fail, we want it to be as less ideal as possible. That means at low temperatures and high pressures. So let's look at the option choices. Large volume. Having a large volume is essentially making this box, resizing it to make it really big, which is the opposite of adding a lot of pressure. So that would, since it's really big, the molecules are really far apart and the intermolecular forces between them are just not as strong. So that's when it becomes more ideal, which is not what we're trying to find. We're trying to find the least ideal because it's failing. High temperature. Again, as temperature goes up, the gas becomes more ideal. High pressure. As pressure goes up, it becomes less ideal. So the option is going to be number 7. Large number of moles, honestly, I wouldn't blame you for picking D because in a let's just say this box, the volume of this box is fixed. If we add more gas molecules, of course, obviously there's going to be so much more, and the intermolecular forces between that many, they're going to add up, and that's going to increase the intermolecular forces. So that means the ideal gas law will fail. That's only assuming that the volume is fixed, that this container is rigid, that will never change. What if we added all those moles and then the container itself started to get bigger? Then that won't really change anything. So if it's specified that large number of moles in a fixed container, then maybe that would have been the right answer. But if it just mentions a large number of moles, we don't really know what else is happening. As for E, this is just kind of a throw off. There's not really anything of the units of R that really have anything to do with when an ideal gas law begins to fail. So the option for number 7 is going to be C. For number 8, we're asked to find which chemical equation would have the equilibrium expression where the constant equals A squared times B. So how do we find what exactly is the equation for the equilibrium constant? How do we interpret this? The equilibrium constant is equal to... Actually, I'll draw an example. We'll just say the lowercase letters are the numbers and the capital letters are the actual elements. Let's say we have an equation like this. In equilibrium. Right? So each of these lowercase numbers could be 1, 2, to any integer, while the letter is some compound. We would write the equilibrium expression as such. The compound to the power of the coefficient of the products divided by the reactants. So products over reactants. As you see, C and D on the product side, A and B on the reactant side. That's how you would write the equilibrium constant expression. So in this case, we don't have a denominator. The only thing we have is a numerator. What would that indicate? That would mean that the denominator is 1. The only way you can be involved in an equilibrium expression is if you are an aqueous solution. So solids cannot be involved. So if, for example, let's just say compound A is a solid, this would not be involved in the equation. So how does that help us interpret equilibrium? The fact that it's divisible by 1 means that both compounds, or all the compounds in the reactants, are non-aqueous. They're all solids. So out of all these option choices, only E has a compound in the reactants that's a solid. Everything else has aqueous compounds in the reactants. So just by that, E is the right answer. But let's fully go over. In fact, I think if my first explanation is confusing, I will use E to draw the equilibrium constant. So the numerator is the products. So the two products we have are A and B. A has a coefficient of 2, so you will have the exponent 2 on A. And the denominator is the reactants, but the only reactant is a solid. So we basically will not have any reactants. We can just divide by 1. That's how we would get A squared times B for our equilibrium expression. So the answer to number 8 would be E. For number 9, we're given that the salt concentration in the Dead Sea is 34.2%, and we're trying to find boiling point elevation due to the sodium chloride concentration. So first we need to find what is the formula for the boiling point elevation. The formula for boiling point elevation is the molality of the solute times the boiling point constant times the Van Hoff factor. So let me explain what those terms mean. So lowercase m stands for molality, not molarity, and there's a good difference between the two. Molality is the moles of the solute over the kilograms of solvent. The boiling point constant, in this case, we're going to find that on the formula sheet, is going to be 0.512. That is the boiling point constant of water. Now, the Van Hoff factor is basically the number of ions a compound can dissolve into. For non-ionic compounds, this will just be 1. But sodium chloride is an ion. It's an ionic compound. It will break up into sodium and chloride. Only 2 ions. So the Van Hoff factor would be 2. How would we find molality? We know that the salt concentration of the Dead Sea is 34.2%. So let's assume the Dead Sea is 100 grams. Right? That means it would be 34.2 grams of salt and whatever 100 minus 34.2, 65.8 grams of water. So we know salt is the solute and water is the solvent. Now we can find out the moles of solute and the kilograms of solvent. So 34.2 grams of NaCl, converting that to moles, you can get the molar masses of sodium and chloride on the periodic table. So 34.2 grams of sodium chloride is 0.585 moles of sodium chloride. 0.585. And now converting from grams to kilograms is just dividing by 1,000. 0.0658. So now a molality will be 8.894. That is the molality. So now we're just supposed to multiply these three numbers. So time that number times 512 times 2. The answer would be 9.107, which is approximately 9.11. So the answer to this question would be A, 9.11 degrees Celsius. For this next problem, we're asked to find which of the members are in the same group on the periodic table. We know groups are the the vertical columns. So we're just asked to find which elements are in the same column. So for A, copper, silver, gold, and platinum. Copper is Cu, silver is Ag, gold is Au, and platinum is Pt. So the answer A would be incorrect. B would be nitrogen, oxygen, fluorine, and neon. These four elements are in the same period, not in the same group, because they're in the same row, not column. Next one is uranium, neptunium, plutonium, and mercury. Again, those are elements in the same period, not in the same row. Uranium is here, neptunium is here, plutonium is here. Mercury is actually not even with them. Mercury is somewhere, I think Hg over here. So far, the first three are out. Carbon, silicon, tin, and lead. Carbon is C, silicon's Si, tin is Sn, and lead is Pb. So D actually makes sense. D actually is the correct answer. And I mean, if you're a Marvel fan, you should just eliminate E right off the bat. So the answer to number 10 is going to be D. For number 11, we're asked to find the rate law for the reaction. So how do we do rate laws? So the rate law is going to always say something like this. There's actually two types. This is the differential rate law. There's another one called the integrated rate law, which it is a little bit more complex, but there's basically three orders you need to know: 0, 1, and second. Here is a differential rate law. So we know the orders with respect to each element. So again, we want in a rate law, the only things that determine the reaction rate are the reactants. The products do not determine reaction rate. So we don't want any answer with nitrogen or water in it. We can immediately get rid of basically almost all of them, basically A, B, and C, because the rate law only consists of the reactants. In a non-reversible reaction. In a reversible reaction, it's different. But for this problem, it's non-reversible, so only the reactants are involved. But now, what is K and what is rate? K is the rate constant, which is basically just how fast the rate would go. Once you get to integrated rate law, you'll start to see how to find K. But basically, we just leave K off like that. And now we'll learn about order. One thing to know is, big misconception, do not associate the coefficient with the exponent. Do not just do this, because this is incorrect. That is true for the equilibrium rate constant, not differential rate law. And they sound the same, but make sure you do not make that mistake. Instead, the way you find out the coefficients is by looking at the order. Second order means you're adding a coefficient of 2. So second order respect to NO means you're squaring NO. And first order respect to H2 would be you're putting H2 to the power of 1, or just leaving H2 as it is. So this is the rate law. So the answer to the question would be, it would be D. Number 12, we're told that 1,026 kilojoules of heat increase the temperature of a sample of seawater from 40 degrees to 80 degrees. If 10,026 kilojoules of heat is added, again, what will the final temperature of water be? So, one thing I want you guys to know is there are two parts to like when you're heating up water. Anytime you're increasing the temperature and anytime you're changing phases. So water, let's just say this is a sample of how the water will go. Initially, you are a solid. Here you're a liquid. And then at the very end you're a gas. And then this is the heat, the energy you're adding. So as you add more energy, you're going to be, or actually this is temperature. So as you increase the temperature, there's going to be a point where like, wait one sec, my bad guys, it's inversed. Temperature, energy. So as you add more energy, there's going to be points where these, like you're going to see these flat lines where the temperature will not change. And this is because it's undergoing a phase change. So see this flat line over here? That's when it's going from a solid to a liquid. This flat line here is when it's going from a liquid to a gas. During phase changes, the temperature will not increase despite your adding energy to it. So in this case, we know 1,026 kilojoules increase the water from 40 to 80 degrees. 40 and 80 degrees falls under the liquid phase. That would not be there. Both of those would be here. And water is liquid from 0 to 100 degrees Celsius. So if you go from 40 to 80, we know 10,026 kilojoules will increase by 40 degrees. If we add another 1,026 kilojoules, you would think it would go again another 40 degrees, 120. But remember, when you're changing phases, the temperature is not going to increase. So, despite adding this much, you're not going to reach 120 degrees because a lot of that energy is going into actually boiling the water. And we can mathematically calculate this. The formula that you're going to be using most often for these types of problems are Q equals the molarity. Oh, no, not the molarity. The mass times the specific heat constant times the change in temperature. So, in this case, we know we have 1,026,000 joules. The mass we don't know. The specific heat of water is given to us here. 4.184. And the change in temperature. You're going from 40 degrees to 80 degrees. That's a 40 degree change in temperature. Solving for the mass. We know the mass of the water is 6,130.49 or 497. But now we want to find what's the final temperature of water when it goes from 80 to 100 and then once it boils. So when you go from 80 to 100, because now we don't want to just go straight from 80 to 120 because it's going to boil. So 80 to 100, that's a 20 degree change. So 20 degrees here. Still, it's in the liquid phase, so you have 4.184. And the mass, we just calculated the mass of of water. So 6,130. That would take 513,000 joules. That's how much it takes to go from 80 to 100. So we have 1026 kilojoules. So just subtracting them, we will have, okay, so that's exactly half the energy like you to get from 80 to 100. So you would have this many joules remaining. You want to, now we don't want to see how much energy does it take to boil water. To do that, it's actually a little easier. It's just simply the mass times the boiling constant, which I forgot how the symbol looks, but, or actually, yeah, the heat of vaporization. So in this case, it's 2,260. So the mass times the heat of vaporization. So again, 6130.497 times 2,260. One sec. Yeah. You would get a number far beyond the boiling point. You would get 13854,923. So that means the amount of energy would not be able to boil the water. So meaning 100 degrees, the water would stop at 100 degrees because it does not have enough energy to go past this many joules. So the answer to this question is going to be D. Everything else is wrong because A, it's not going to go up to 120 because it has to boil before it starts to go up to 120. Not here because it's not able to pass 100 degrees Celsius because the boiling point, the amount of energy is too high. Not less than that because we know it can definitely reach 100. And E, it's not going to boil away before it reaches that. So the answer number 12 would be D. For number 13, we're asked, is carbon dioxide an acid, a base, or neither? According to the Arrhenius definition. So what is that? Arrhenius basically states that if a compound releases H+, it's an acid. If it releases OH negative, it's a base. So, does carbon dioxide release H+ or OH negative? Now, you might be looking at this problem and then going immediately something along the lines of neither, because CO2, where's the hydrogen coming from in CO2? But if you think about it closely, when you dissolve carbon dioxide in water, this is what's going to happen. You're going to form carbonic acid. And carbonic acid does release hydrogen. So the answer would be E. Think of, for example, acid rain. When the carbon dioxide from any disaster like a volcano mixes with rainwater, that's what forms acid rain because of the carbonic acid in that water. Same thing with blood acidity. Once you get way too much carbon dioxide building up in your body, that's how your blood starts to become acidic and the pH goes down. So carbon dioxide on its own isn't acidic, but when you dissolve it in water, you'll form carbonic acid. For number 14, we're asked to find the number of atoms in one formula unit of potassium dichromate. So this one is really just about, do you know what dichromate is? If you don't, dichromate is chromium 2, oxygen 7, negative 2. So we know potassium is just K plus 1 with a positive 1 charge. Well, dichromate has a negative 2 charge. And we know we want the charge to balance out, so we should have 2 potassium for every 1 dichromate. So the formula should look something like this. K2Cr2O7. Add the 3 numbers up, you're going to get 11. So answer number 14 is C. For number 15, we're asked to find the difference between an electrolytic and a galvanic cell. A galvanic cell is basically a cell that, okay, wait, actually I'll draw it on the bottom. With two electrodes, such that the electrons will flow without any need for an external voltage, and there's a salt bridge between them. So we have two solutions, and we have like two elements. For example, let's just say that this be zinc and this be copper. Electrons will start flowing from like one electrode to another without the need of any sort of external battery source. So what does it mean that if it does not need the external battery source? That means that the reaction is spontaneous. Galvanic spells are spontaneous, and they have a Gibbs free energy that's negative. They do not need any external energy. And when that happens, when your reaction does not need any external energy, you're basically having a positive cell voltage. So your cell voltage would be positive. An electrolytic cell, on the other hand, is a cell that requires a battery to force electrons in the other direction. So I'll just draw a battery right here. And in an electrolytic cell, you're gonna have a negative cell potential because the reaction is not spontaneous. Gibbs free energy is greater than 0. So galvanic cells are generate positive voltage because they're spontaneous. Electrolytic cells do not generate, and they generate a negative or 0 voltage because they are not spontaneous. Let's look at everything else. Both solutions contain electrolytes. That is the main driving force between the two. B is incorrect. Galvanic and electrolytic cells are two different things. C is incorrect. D is incorrect because electrolytic cells cannot give off light. And E is incorrect because, well, first of all, this is the chemistry section. We've finished biology, so you should really not be seeing those things again. Also, these are things, they're not cells as in like cells and organisms. So E is incorrect. The answer to number 15 would be C. For 16, we're asked to find which one of these is not a valid empirical formula. An empirical formula is a formula where every atom in like a compound has the smallest number of coefficients, pretty much, or subscripts. And what I mean by that is like the numbers, the subscripts, they all must have a greatest common factor of 1. So let me explain what that means. So between A, they both have 1 carbon, 1 hydrogen. The greatest common factor is 1. Here, 1 carbon, 2 hydrogen, the greatest common factor is 1. Greatest common factor is 1 between these guys, and the greatest common factor is 1 between those two. But what about C2H4? The factors of 2 is just 1 and 2. The factors of 4 is 1, 2, and 4. So C2H4 has the greatest common factor of 2. The most simplified version would be if you divide 2 with both these, so you would have CH2. This would be the empirical formula. And C2H4 is actually the molecular formula because it doesn't have the greatest common factor of 1. So the answer to number 16 would be E. For 17, we're asked to find the silver ion concentration of a saturated solution of silver oxalate. When you dissolve silver oxalate in water, what are you going to get? When you dissolve any salt in water, first of all, you're going to break it down into its ionic compound forms. So in this case, you break it down into 2 silver and 1 oxalate for every 1 silver oxalate you dissolve. Now, unlike salts like NaCl or AgCl, like where you drop it in, it's going to immediately dissolve. Some salts like this, they're not going to dissolve as fast, and in this case, it's a fully saturated solution. So, meaning there's going to be a reversible reaction that's occurring. So it's the solid salt is going to dissolve into aqueous compounds at the same rate as the aqueous compounds are going to form into the solid salt. And in such a situation where the rate, the forward and the backwards rate is equal and there's no change in either concentrations, we're asked to find the silver concentration. We can do this by drawing an ice table out. So we don't know the initial concentration, the initial amount of the salts, but the thing is, we actually don't even need it. Like I said in a previous problem, oh shit, I forgot to mention, this is solid while the other two are aqueous. We don't need this at all because solid compounds are not going to be found in an equilibrium expression. So this could just be X, right? We don't even care about it, but let's call it X. And let's say you only added the salt initially, so there are no ions in the solution. That's the initial. C stands for change. For every 1 mole of let's just say A, for every 1 mole of silver oxalate that's being dissolved, you're getting 2 moles of silver, and you're getting 1 mole of oxalate. So for every A moles of silver oxalate that's being dissolved, you're getting 2 moles of silver and 2 A moles of silver and 1 A mole of oxalate. So E would be just X minus A, 2A, and A. You're just adding and subtracting the numbers up. Remember, an equilibrium expression has to deal with this last part. So K has to deal with the products, which we know are silver and oxalate. We know there are 2 silver involved, so you would square the silver because there's 2 involved. And there should be nothing in the denominator because the reactant is a solid, so we can ignore the denominator completely. So what's next? Well, let's replace the silver with 2A and the oxalate with A, because these are the concentrations that are going to appear at equilibrium. Now we have this general formula, and we can expand that and multiply. We'll get 4A cubed. Now, what do we do with that? Well, we are given the rate constant. We are given KSP. So 4A cubed is equal to KSP, which is 5.4 times 10 to the negative 12. So plug that on a calculator and solve for A. You will get A is equal to 1.11 times 10 to the negative 4. Now, you might immediately circle A and call that done, but be very careful. A is the equilibrium concentration of oxalate. 2A is the equilibrium concentration of silver. So we have to multiply A by 2. So we want 2A. Let me clear up a little bit of work here. We want 2A because that's the silver concentration. 2A is 2.21 times 10 to the negative 4. This right here is the silver concentration. So the answer to number 17 would be B. For number 18, we're asked to find the molar mass of caffeine. So again, all we need to do is for molar mass is to find the total number of elements and the molar mass of each element. So in caffeine, there's only 4 elements. There's carbon, hydrogen, nitrogen, and oxygen, as shown in the figure. The hardest part about this problem is knowing where the carbon and the hidden carbon and hydrogens are, because in these ring structures or like any of these like stuff you'll see like with organic molecules, the carbon and the hydrogens will sometimes be hidden to make it like easier and more simplistic to draw. Right here in this corner, this is actually a carbon. So I'll draw in green all the carbons. There's a carbon here, carbon here, carbon here, carbon here, and a carbon here. Now how do I know there's a carbon? I mean, pretty much any of these points, any corner, you'll see there should be a carbon there. Another thing you want to watch out for is how many bonds the carbon has. We know carbon can form 4 bonds. It always wants to form 4 bonds. Here, carbon does have 4 bonds. You have 2 on oxygen, you have 1 on each nitrogen, so it's 4 total. Here, it's 4 bonds. This one over here, I should put the pointer. This carbon here has 4 bonds. This carbon here has 1, 2, and then 2 here. Same thing, this one. This one has 4 bonds. This carbon here, you have 2 double bond on the nitrogen, single bond on this nitrogen. That's 3 bonds. You need 1 more bond. And this is what I mean by those hidden hydrogens. Because it turns out there's actually another bond going out here. But what is that bonded to? It's bonded to a hydrogen. So there's actually a hidden hydrogen right over there. Now let's count the number of each element. Carbon, you got 1, 2, 3, 4, 5, 6, 7, 8 carbon. So just 8 carbon. Hydrogen, you got up in pink this time. 3, 6, 9, 10 hydrogen. For the nitrogen, you have 1, 2, 3, 4 nitrogen. And for oxygen, you have 1, 2. So we got every element down. Now, simply just using the periodic table, we can just multiply all these numbers by the respective molar masses. So carbon has a molar mass of 12.01. So 8 times 12.01. Hydrogen, doing the same for hydrogen, doing the same for nitrogen, doing the same for oxygen. If you do the math right, you should get a molar mass of 194.22. So the answer to number 18 would be A. For 19, we're asked to find how many pi bonds are in the caffeine molecule shown. So, what are pi bonds actually? So, we have the 3 different types of bonds, single, double, and triple, right? And we have 2 different categories, sigma bonds, pi bonds. So so every bond has 1 sigma bond. So for example, a single bond will have 1 sigma bond, double bond will have 1 sigma bond, triple bond will have 1 sigma bond, and this will extend for any type of bond. You'll have 1 sigma bond. Pi bonds will start at 0 for 1 pi bond for a double bond, 2 pi bonds for a triple bond, and then that will go 3, 4, 5 all the way down. So we're asked to find how many pi bonds are in the caffeine molecule shown. We know single bonds have no pi bonds, so we can ignore single bonds. And we know caffeine only has single and double, so there are no triple bonds, so we don't need to worry about that. Only thing we need to worry about then is the double bonds. Each double bond will have 1 pi bond. So if I get rid of all this, how many double bonds do we have? We have 4 double bonds. So that means we should be having 4 pi bonds. So the answer to number 19 would be 4. For the final question, our current periodic table lists 118 elements, but is it possible for there to be any undiscovered elements in between the elements listed in the periodic table? This one is a sharp no, and the reason for this is because we accounted for all the possibilities from elements 1, hydrogen, to elements 118, again, Hassan. Those are the elements we accounted for. We theoretically could have more if we just like with more reactions above 118, but for now, there are no more elements in between those. We accounted for all the nuclei possibilities from 1 to 18. So the answer to number 20 would be E. And that is the end of the chemistry section. I think this was quite a long section, and I really hoped that my guide on each question is detailed enough for all of you to understand. If you guys don't, feel free to write it down in the comments, and I'll be more than happy to explain it to you. And I hope this was, I just hope this was a great guide on these 20 questions. I'll be putting my physics video out in maybe 1 or 2 weeks, so just be on the lookout for that. Anyways, I hope you guys have a great rest of your day.